So let me start by saying that these talks are part of a course which Gibran from CS organizes every year. And this year, I talked to him that maybe we should discuss in this course topological quantum computing, and he agreed. And I'm very grateful to him for allowing me to speak in this course. Being a complete non-expert in quantum information, I think it's very gracious of him to let me speak. And when I looked at his outline, I realized that the way this course is usually run is that the students prepare and give lectures. Is that?
It's like 50-50.
50-50. So that makes me even more happy because I'm also learning this stuff as I speak. So consider me part of those students who are going to speak in this course. So topological quantum computing is all about non-abelian anyons, using the properties of non-abelian anyons to implement quantum computing. So in my set of lectures, I will try to do two things. One is taking non-abelian anyons models and then study how to compute some quantum computation, how to implement quantum codes given a non-abelian model. But I will also like to discuss a little bit how do these non-abelian anyons arise in actual physical materials, and what kind of materials have these topological properties which support these particles which are needed for topological quantum computation. Obviously, I will not be able to do much justice to at least this second goal of describing these materials in detail, but I hope that we will be able to learn at least some ideas behind those. Now, in this course, there are many CES students. There are quite a bit of audience, which is CES students. So thought that I'll start with some very basic introduction of some physics ideas which will be needed in this course. So today's lecture, I'll discuss Maxwell's equations and the Babar phase. So the idea is I want to discuss a little bit how to describe quantum mechanics when you have magnetic fields around. And since I'm not assuming anything, so I'll start with describing how is a magnetic field is discussed in this context. And I hope that I'll end by discussing the Babar phase. So this Babar phase is at the heart of all of these topological phenomena which arise in these topological materials, be it topological superconductors or quantum Hall effect. So I thought this would be a good start to discuss. So let's discuss what are the Maxwell's equations. So everyone is aware that you have heard at least in high school that there are electric and magnetic fields, and they affect the motion of charged particles. And these electric and magnetic fields have their own dynamics. So they are described using certain partial differential equations. So there are a set of equations which are called the Maxwell's equations, which govern the dynamics of these fields. So what are these equations? One of them is about the electric field. So it's telling you, essentially, I'll be very quick. This is the Coulomb's law. So the consequence of this is that for point charges, the field is of this form. So all these pictures you have seen, that you have a point charge, the field will be going radially outward. and it falls off with the distance squared. And this is the differential form. If you want, you can also write integrating it over a surface. You'll get this if you have a point charge, if you have charge inside. So this is the Coulomb's law, which we study in high school, just written in using some differential equations. Then there is this Faraday law. So what this is essentially saying is that when you have changing magnetic field, then it gives rise to some curling electric fields. So this again, you must have seen at some point that if you have a magnet like this and you move it up and down, you induce electric currents in these coils. And this law is at the basis of all this dynamos and motors and whatnot. So you use changing magnetic flux to cause electric field. That's what it's saying. Then we have the Ampere's law. This one also you have seen in school. They tell you, so this is the electric current density. So you have, if you have current in a wire, it will produce a curling magnetic field around it. So this is, we are also familiar, and this is the form of it. There is this extra term, Maxwell's invention, which makes it kind of very symmetric to this. So it's telling you a changing electric field is going to also induce a magnetic field. And then there is this final one. So like this is an analog of that. This one is an analog of that. So this is essentially saying that there are no monopoles, no magnetic monopoles. So what it tells you, that in magnets, your fields are, they don't have an ending or starting points. They go inside, they come out, or like over here, they keep circulating. There is no ending or starting or ending point. I can't break this magnet, take the south pole away, and get this kind of a Coulomb field for the magnetic charges. Now, with these given, I want to set up quantum mechanics. So how to do quantum mechanics when you have electric and magnetic fields around. So here, the electric and magnetic fields, they would not be subjected to quantum rules. They will be a background kind of a potential. And a particle which is moving in these fields, that will be considered a quantum particle. So what I need to do, I need to get, if I want to quantize such a theory, I need to have written the equations of motion in a Lagrangian or Hamiltonian form, because that's the only way I can get the quantum mechanics. So this is the classical law of motion This is called the Lorentz force law. So the acceleration, this is the force, it responds to the electric field by direct coupling of the charge, responds to the magnetic field through velocity with a cross product. So we have to get this force law, but through a Lagrangian. It turns out that there is no way that you can find a Lagrangian in terms of electric and magnetic field, which will give you this directly. So you have to do something. So really what you need to do is invent what is called the potentials. Electromagnetic potentials. So they are needed if you want to write a Lagrangian and therefore then get to quantize it to get a quantum description of a particle moving in electric and magnetic fields. Now, what are these potentials? So, what you do, by the way, first of all, let me just mention something, emphasize it a little bit again. So over here I said that this thing is saying that there are no magnetic monopoles, there are no magnetic charges. So you can't also have a current of magnetic charges. So if you look at this thing, this has electric current on the right hand side. If there was a symmetry, there would be magnetic current on the right hand side of the Faraday law, which is not there. So two equations have sources. So this has electric current as source, that Gauss's law or Coulomb's law has electric charge as source, but these two equations, they do not have sources, which is a good thing because we're going to use these sourceless equations to construct these potentials. So this equation means I want to have a field whose divergence is 0. This is automatically solved if I define a new field A, a vector field again, and consider B to be the curl of that, because the divergence of a curl is automatically 0. So this guy is called the vector potential. Now I take the other sourceless equation. And I just replace this over here. This time I'm getting a curl of a field which is 0. So this means I can take this to be the gradient of a scalar. Then this equation will be automatically satisfied. So I define this minus is just by convention. This whole thing to be minus del phi. And call this the scalar potential. So my B field is written like this in terms of potentials, and my electric field is written like this in terms of potentials. Maybe just one comment for anyone who has studied this theory and remembers a little bit, that my units are such that I don't have any constants hanging around. Natural units, C is 1 and mu naught, epsilon naught, they are all 1. So now your problem has become that you have this set of fields. Instead of 6 components, now I have 4 components, which I have to solve for. And what is the dynamics which governs them? I put these back into the other sourced equations. So when I put them in the sourced equations, it's not very important, but let's just write it down. So I'm just putting this E in the Coulomb's law. So I get minus del square phi. I change the order of the derivatives. So this is the Coulomb's law. And when I put it in the Ampere's law, I get del cross B is del cross A. For E, I get minus del phi, but E also has minus dA by dt. So I get the second derivative. And then just using this vector identity, this can be written as we won't be concerned with these equations much. But the point is that 2 equations you automatically solve by writing electric and magnetic fields in terms of these potentials. So 2 are automatically solved. The other 2 then become your equations which govern your dynamics. So you get solutions from here, and once you have solution for phi and A, you can construct your electric and magnetic fields. Those are your physical fields. Those are the fields which you measure, because these are the fields to which your particle responds, any particle. Now, but there is a slight problem. Well, no problem for now. I'll discuss that later. Now, why did I make these potential? What did I gain out of it? The first thing and most important thing for me is that I will be able to write a Lagrangian which gives me my desired equations of motion. So if I take this Lagrangian, for a particle, this dot is derivative with respect to time. This is like V. And if you compute the Euler-Lagrange equations, you can show that you get your desired equations of motion. I'm not going to do that. Instead, let me find the Hamiltonian corresponding to this Lagrangian, because that's more relevant thing for us, because once we have Hamiltonian, we can define the quantum dynamics by implementing it on a Hilbert space. So what's the Hamiltonian from here? So this is a reminder for those who have taken classical mechanics and those who haven't. Let me just say a few words. Lagrangian is a scalar function of your basic variables, which in this case are these position variables of your particle. So these are your dynamical variables whose dynamics you are trying to get, whose dynamics you are trying to describe. So Lagrangian is a function of x and x dot, and it's a scalar, gives you a number built out of these, and it should have all the symmetries which you require in your theory, and you do a standard operation maximizing this Lagrangian to get, putting this Lagrangian in action and maximizing that to get the Euler-Lagrange equations. And Euler-Lagrange equations are what we usually call the Newton's equations. But given a Lagrangian, there's another way to get the equations of motion. You do a transformation on it and convert it into a Hamiltonian. So the easiest, let me just say it in easiest words, what you are supposed to do. You're supposed to invent new variables, Pi, and do this process. And then you express it eliminate the velocities. Where these Pi's are defined this way. And they are called the canonical momenta. In the simple cases, these canonical momenta are your usual momentum, m times v. But this is the process to get a Hamiltonian from a Lagrangian. So let's apply this to our given Lagrangian, which I have just wrote. And what we get is, first of all, what are our Pi's? So I'm taking a partial with respect to this. It's like a x square. So I get mxi dot. For each coordinate, I'm getting a canonical momentum. But I have a x dot here too. So in the canonical momentum, you also have the vector potential appearing. The simple partial differentiation with respect to x dot, xi dot. So this means these guys which I have to eliminate are these. And when I write my Hamiltonian, which is Pi, so this thing, and subtracting the Lagrangian. So maybe just see what I did. Maybe I should have mentioned one more word for the uninitiated. When I write something like this, I am always assuming a summation. So this is essentially this dot product, not essentially exactly this dot product. So what I see is that these guys cancel, and I get a half of this is subtracted away from this. So a very simple Hamiltonian appears, but I have to have Hamiltonian written in terms of the momentum, not in terms of the velocity. So I have to replace this guy. So when I do that, I get two m's appear down, one cancels with that, and I have by square I mean I'm taking the dot of this guy with itself. So I've just now switched from I notation to vector notation. So this is the electromagnetic, I shouldn't say electromagnetic, this is the Hamiltonian of our particle moving in electric and magnetic fields. But you have to write it in terms of A and phi. There's no other way around. You cannot directly write it in terms of E and B. But there is a potential issue with this, a severe issue with it. Q, by the way, is the charge, and so the prescription is this. You want to write the Hamiltonian for particle, find the vector and scalar potential of the field in which it's moving, and replace momentum by minus QA and add Q phi to the Hamiltonian. So what's the issue with this? The issue is the following. Notice this thing. If I change phi so I took an arbitrary function of space-time, a completely arbitrary function, and suppose to get a certain electric and magnetic field I solved and I found the potentials phi and A, and I said these potentials will give me my electric and magnetic field through those formulas. Did I write them? Okay. So I'll write them again. Through those formulas, it gives me the electric and magnetic fields. Then I say, okay, I change my potential and see what fields I get with these new potentials. So formula, so I'm having this new potential. And A dash then the formula for magnetic field was, so what would be the new magnetic field? Is the curl of this new potential but the curl of a gradient, as we said before, is 0. So this is just the old field. Similarly, for the electric field, this was the formula. I have shifted my phi by this, so I get and I have shifted my A by that, so I get so these two cancel and I get my old field back. So that means that this phi and A are not uniquely determined. There's a huge freedom in choosing phi and A. All of them give me the same electric and magnetic field. And my physical results, they should depend on these actual fields, E and B. Phi and A were just my own inventions to solve these equations. Actual fields are E and B. But in these potentials, there's a really huge freedom. This is an infinite dimensional freedom because you have a whole, any arbitrary function defines this. This is called the gauge freedom of potentials. So what is the freedom? That if I shift my potentials by this kind of transformation, these are the gauge transformations. This is the gauge transformation. My physical fields do not depend on the gauge choice. Out of all these various phi's, which one I pick, my physical fields do not depend on them. And you can also show that these laws, which I wrote for the dynamics of A and phi, they are also gauge independent in the sense that if I shift my gauges, if I shift my fields, the new fields are going to satisfy exactly the same equations. So you may ask, okay, so what's wrong? If there is a huge freedom, I can choose any one of those and do my calculations, because in the end, I care about E and B, and E and B do not depend on those choice of gauges. This was all good in classical physics, but when you look at the Hamiltonian, you find a potential problem, because the Hamiltonian is directly written in terms of A and phi, not E and B. So if I change A and phi with a gauge transformation, the new Hamiltonian, if it's different, then I'm getting a different dynamics for the same electric field, which is not making any sense. So we want no observables to depend on gauge choice. Or you can say observables are gauge independent. So we should at least first check what happens if I gauge transform my Hamiltonian. Well, before I gauge transform, I should say, I should write it this way. So let's look at the Hamiltonian here. So I want a representation of it on some Hilbert space. You can use your common representation on the L2 functions. And over there, the prescription is, this is Dirac's prescription. That you look at your canonical momenta, because our Poisson brackets are these. As soon as I define my canonical momenta, this goes to so I want a representation of this algebra. And what is important to note, so I want a representation of this algebra, so what would be the representation? Your usual one. You take your P and your x's are multiplicative. Then you can represent them on your space of functions as an L2 space. So that means the Hamiltonian in this representation, which is the most familiar one, would be written like this. And now, since I have chosen a representation where these are just functions, so I can now easily do my gauge transformations over here and see what happens. So if I do that, I get this H goes to H prime. So I'm replacing this A by A dash. So I get and this is being squared, and then I have this phi being shifted like this. So now this doesn't look gauge invariant because there's nothing to cancel this and nothing to cancel that. But we have to remember that our wave functions themselves have a gauge freedom. Gauge freedom in exactly this sense that your wave functions or state vectors, they are waves in the Hilbert space. The actual vector you pick up, that's not important. You can always multiply it with a phase. That's allowed. And just like over here, these gauge potentials are unobservables. They don't have physics. That phase, at least in most senses, do not have physics. So what you have is, so suppose I make a gauge transformation here. I feel like that I'm in trouble. My Hamiltonian has changed. But actually it hasn't, because I observe that if I at the same time make this gauge transformation on my wave functions, then for this is the old wave function, this is the new wave function. Now if I apply my Hamiltonian, because what I can do, I can look at my Schrodinger equation, what happens to that. So if I apply my Hamiltonian on this wave function, you're going to have these kind of things. Del psi, and you have the phase outside, and once you have psi and the phase is still there. So I get q lambda. So application of this guy generates, and I have not q lambda, q del lambda. Right? So I just applying this on this guy. Once you differentiate this, once you differentiate that. When you differentiate that, you get this term, which is exactly that term which you wanted to cancel. So when you change the wave function and simultaneously as you change your vector and scalar potential, and this term will cancel with the time derivative of the Schrodinger equation. So you find that with this gauge freedom, that A goes to this, phi goes to this. Did I use it with the minus or plus gauge transformations over here? And psi going to this is the gauge freedom of QM. With these gauge transformations, your theory will be gauge invariant. Your results will not depend on what gauge you choose. So this is very important because we cannot do quantum mechanics without potentials, but with potentials, you are forced to introduce a gauge freedom. And you have to keep in mind that the theory is invariant. It shouldn't say even it's not symmetry in the usual sense. It's just that all of these are describing the same theory. Now, let me go back to the any questions so far? Ji.
Sorry, it's like me trying to make some kind of connection to quantum computation. Like gauge freedom would exist in classical field theories as well, right? So now if I want to use a standard conversion from quantum computation to quantum mechanics, that any physical systems evolution can be thought of as a computation.
Any physical system?
Systems evolution can be thought of as a computation. What would be, like, what would gauge independence translate to in the language of computation? I
think it's best to think of it as not a symmetry. It's not giving you a symmetry in the usual sense. It's just that you have a redundant description of the same thing, because your actual fields were E and B, and you chose to represent it with phi and A because you were forced to. And you are left with a huge redundant description, and what you can do, you can pick one. You can pick one gate, you can fix one gate, and describe your dynamics with that. But you have to keep in mind that I can change the gates, and the same dynamics can be described in some other gates. So it's like different representations of the same process.
Like, just what kind of consequence might that have in an algorithmic sense? As a
Because, well, the thing is, if you have a concrete algorithm, I would imagine that you mean a particular physical process. And what this is saying, that the physical process do not depend on these. So I don't know, unless there's a very specific context, it would be hard for me to say. But it will become, as we go along, it will become clear that this kind of constructions have various consequences. So for example, this non-abelian nature, even the abelian statistics of anyons, that is closely related to these, what's happening over here. So, but I have set up the problem of quantum mechanics with electric and magnetic fields. There was a potential problem which we also solved. But let me make a kind of detour, which will later on turn out to be relevant, and just a intellectual curiosity. So these were my equations. Let me just quickly write them again. And as I mentioned before, that if there are no sources, so I'm talking about vacuum. जी. ये कैसे कैंसिल होगा? Oh, because you have Schrödinger equation has two sides. So these are my equations, and I said, like, if I don't have these, so I'm not near sources, then these look extremely symmetric. And actually, it's like you rotate in EB plane by 90 degree, B becomes E becomes minus B. Then this equation goes to this. And that equation goes to that. So there seems to be a symmetry there. And one might wonder that if there are sources, can there be a symmetry? Well, there could really be a symmetry very easily if I had magnetic charges. So rotate in the magnetic, in the charge planes as well. And you will have symmetry in the presence of sources as well. And also you might wonder that why there are no magnetic charges. We just declared that there are no magnetic charges. Otherwise, electric and magnetic field, they look very symmetric. Like when you have light propagating, you have electric and magnetic field. And as you can see from vacuum equations, they are affecting each other in a very symmetric way. So why there are no magnetic charges? What goes wrong if I have magnetic charges? Maybe they are, we haven't found them because people didn't find electric charges for a long time, I suppose. For the most part of human history, people didn't know about electric charges. And if there are magnetic charges, it's easy to write, correct the Maxwell's equations. You just put the sources for magnetic charges. And people look for them. So far, no one have been able to find them. Apparently, there was an experiment which gave a signal once, and the guy who was observing the experiment, he swears, and I mean his circuit also showed, but one observation doesn't count statistically. So anyway, so one can ask, what if the magnetic charges are there? What happens then? Doesn't seem like a very big jump of faith. Well, one thing seems like maybe that's why the magnetic charges are not there, because if there were sources, I depended on sourcelessness of this equation and this equation to create my potentials. Then I won't have potentials. And if I don't have potential, I won't be able to do quantum mechanics. So maybe there are no magnetic charges. That's why. But let's keep pushing the idea that what if there are magnetic charges, and can I salvage the situation for quantum mechanics if there are magnetic charges, or as they say, magnetic monopoles? So far in our world, even if we believe that there are no magnetic charges, it was Dirac's construction, Dirac's ideas. Dirac thought, well, I don't know what he thought, but let me just imagine this is what he thought. So if you have a coil, current carrying coil, then you have magnetic field going like this. So he imagined, and if I make this coil longer and tighter, then this field will shoot further away, like that. So he imagined that what if I make it very tight, keeping the flux constant, flux through this coil constant. What would that mean? You're making the area small, so magnetic field is getting stronger inside. So you make a very tight coil, and you don't want the fields to come back, so you let it go to far infinity. Then very easily you can compute that the magnetic field of such a coil would look exactly like the magnetic monopole, like an electric charge. Except that along this string you won't have what you usually expect. Rather, the field is going in this direction. Not only is going in this direction because you have to take the limit, you have singularities, singularity here, a string singularity. Field is blowing up over there. Well, with this kind of construction, you can say, well, if I have a particle going around here, this is a infinitely thin string, the cross section is 0. It's never going to touch. And if it never touches this singularity, then who cares? So this thing works exactly like a magnetic monopole. So it seems like even if I don't put the sources, in the classical theory, I can kind of create the sources for magnetic monopoles, which will work just like the electric charges. Now, then, but what to do about the quantum theory? Quantum theory does need the potentials. So Dirac asked, okay, how can I create a potential for such a thing? You can again say, maybe not much trouble. I have this field. I can try to look for a potential for this magnetic field, which creates this magnetic field. What I will be sure, because there is a singularity here, that the potential will not be well defined over here. It will not be defined. It will blow up here. So what to do with that? Well, then you can say, I can consider a second situation. So one is this. This gives me, let's suppose, I can stop here. I can go up to string, but let's suppose I stop here. I can probably construct a potential for this kind of situation, because this is just going to be my known results of the coil potential and just taking a limit. Then what to do over this region? Well, because I don't want to observe this coil, I want to construct something which does not have a coil. So then I can consider this complementary situation where coil is up over there and the charge, well, I should make it at the center. At the center of this circle. So magnetic monopole is kind of sitting here. And then I can construct the potential for that Y, which I can stop here. I'm just writing it on a sphere because it's going to have a spherical symmetry. So now you have two potentials. Let's call it, this works everywhere except in the south pole. So let's call it AN. And then you have potential corresponding to this configuration, which works everywhere except in the south pole. Oh, this works in the north pole. This works in the south pole. Right? Because this guy has a singularity over here, and that guy has a singularity over there. So what then I can do, I can use for the north part, I can use that, and for the south part, I can use that. But they're going to intersect at some point. You cannot stop at a line and then you have to tell what happens on the boundary. So you have to patch them properly. And as you can see, that there's going to be a significant part where they both overlap. And you don't have the choice of cutting off this overlap, because you will have to have overlap at least in some strip. So then you have to tell what happens across this overlap, which one to choose, how to do. So you have to do this swing. So what's actually happening over here, you are essentially saying that this vector potential, it kind of becomes a bundle which does not have a global section. You have to have local sections and you have to sew them together. All of this can be lifted and described in the language of fiber bundles, which I hope we will be able to discuss someday at some point, but I don't think in this course. But that's what's going on. But in simple terms, it's just that you have a potential on the top part, a potential on the lower part, because one single does not work. You need two. And then you have to sew them together properly to get something which works.
So just a clarification, like why does a single not work?
Oh, because there's a string singularity.
And there's no way we can kind of somehow map it to a singularity like you have an electric charge, just at the point charge. Like in an electric field, you would have singularity at the point charge, right?
Yeah, over here.
And then in the magnetic case, would it not be possible to take the entire string and somehow build a construction that maps it to just a point?
No, because the singularity will be extended. You can say, I don't care if there's a singularity over there, let it be there. But the point is, if a quantum particle you have to describe, quantum particle doesn't care, it's not a point particle, it's a wave function. So you have to tell what happens in these regions, what happens to wave function over there. And if the potential is singular, you won't be able to describe the wave function. So there's no problem at classical level. The problem arises only at quantum level. And you can see this problem at quantum level in many, many contexts. So the way I'm describing is only one context. You cannot give a wave function with this singularity present. But there are other ways you can see that as well. So for example, you can do interference experiment. So you might say, okay, there's a string over here, and I don't care if there's a string. But if you have a quantum particle, and you say, I want to forget about the string. If you have a quantum particle and you make interference experiments around the string, you will see some phase will be picked up, and by interference experiments, you will be able to tell the presence of the string. But the cleanest argument is that the wave function is not well defined. So I have to give this AN and AS. Well, Dirac did it. Not that hard to find, but I mean, obviously the idea is very hard to come by. So this is the vector potential in the North Pole. By the way, I don't need the scalar potential because I'm just considering the magnetic field, and magnetic field does not depend on the scalar potential. So this you can see, if I put theta is equal to pi, this is singular, because I have a 2 and 0 over here, but at theta is equal to 0 is regular, because you have a 0 over 0, and if you take the limit, it's regular. So it has singularity, this guy, along negative z-axis. While this guy at theta equal to 0, this is singular. So this has a singularity. Along the positive z-axis. And why these work, if I just compute the curl of this field, and for here you just have to open the Wikipedia page for all these curl, del, divergence formulas for spherical coordinates. I have them written up here, but I mean, no one remembers them. You always have to open the Wikipedia. And so there's this long formula for curl, but you have to keep in mind that you have only the, I'm writing it in spherical coordinates, you have only the phi hat component. And that also depends only on r and theta. So I'm only writing those terms which survive. So for a vector field written in spherical coordinates which has only a phi surviving component, this would be the formula. So this gives me, when I plug this in, sin theta will cancel with this, and this is just a constant. This r also comes out. Let's see what becomes of this guy. So r's cancel, and I have just well, actually this is also going to 0 because there is no r. So this derivative gives me a sin theta which cancels with this. So I get this field. This is the B field. And this is exactly what I wanted. Maybe I should write it here. So this is the Coulomb field which I wanted. So this potential gives me the field of a magnetic monopole. Similarly, same thing happens for the A south. You get the same field, except that these formulas don't work on their corresponding singularities. So the question is, on the overlap regions, what happens? So if I just compute the difference, the fairly simple formulas, so that means I get this. I just add this term to the south, I get the north. But I can notice this. that this can be written as the divergence of a function, of a scalar. So that means that this guy and this guy are related to a gauge transformation. So it's just that I cannot choose a global choice of gates. I have to stop somewhere. So you have two patches, and you need to use two patches, and where they overlap, there you sew them using a gauge transformation, which will not affect any physical observables. So you can note this, that if I compute this, then again the horrible formulas only this term survives, and that gives you exactly that term. So there's also this term used, that this is a pure gauge. Pure gauge means a field which is gradient of a function. You can compute, for example, okay, before I do that, let me come to the wave function. So because A naught only does not work on the string, so my wave function cannot be defined in terms of one of those. So wave function itself will have two local sections, and they will also have to be passed together. So you will have south and north. But our prescription tells us what we just worked out a little while ago, that if you are making a gauge transformation, then that translates onto the wave functions as well. So this gauge transformation on the south potential gives you the north. So if you make a gauge transformation on the south wave function, the same gauge transformation using the same lambda, you'll get the north wave function. And so what is our lambda in this case? So lambda is supposed to be a function of r theta phi, but it's just 2g phi. So this function is discontinuous, because once you come back from 0 to you're at the same point, your value is taking you have two values over there. It's not single valued, which is crucial. You need this, otherwise this will not work out. I'll show you in a second that there's no way out of it. But the wave function, that needs to be single valued, because you have to put it in the Schrödinger equation and you have to take its derivatives. So you have no choice over there. You can't have two values of the wave function at the same point in space time. that means this object should be single valued. So as phi changes by 2 pi, if you have a phase over here and this guy is not being single valued, it better be a multiple of 2 pi so that the wave function itself is single valued. So that would mean we just have to see what is gamma. Gamma is I'm just speaking from here. So I change phi by 2 pi. That must be equal to there's a Q. The original value plus iota 2 m pi. Right? Remember, this Q is coming because you have a charge there which is moving in this field of the monopole, and G is the charge of the monopole, is the magnetic charge. So this gives me what? I just have to pick these terms. This and this cancel, and this term gives me, so this pi's cancel, I cancel, and I get QG is m h bar over 2, and m is integer. So this is called Dirac's quantization condition. And what it says is that the product, if a magnetic charge existed ever, its product with electric charges will be quantized. It can't be arbitrary.
The Q is यानी जो particle consider कर रहे हैं, जो move कर रहा है उसका charge.
So they cannot be any arbitrary electric and magnetic charges. So if magnetic charge, if there is one magnetic monopole somewhere, then all the electric charges in the world are quantized in some half units, and maybe that's the reason, I don't know, we have these elementary particles have these charges, the quarks and electrons. But anyway, this gives you a quantization, a combined quantization of electric and magnetic charges.
Would you say that this came out of our requirement that the wave function should take one value? Like that was a...
Yeah, but that's a demand because there's no way out of it. The correct way to think of it is that the wave function is it's a twisted fiber bundle which cannot be trivialized globally. So it has two sections, and the sections have to be sewed properly. So when you sew them, the topology imposes on you of those fiber bundles that this must happen. If this doesn't happen, then there will be problem. So in simple words, you are right. We are demanding that the wave function must be single valued. But since it's built out of two pieces, so the demand for single valuedness sues them in a very particular way, which imposes this.
There's no weird kind of us saying, well, you take those two values and create a superposition of that out of those two values to create one single wave function.
No, this is one single wave function. This is not two. One should not think of it as two wave functions, because you have to keep in mind that a state has in it gauge freedom, which is the global phase vector. So states are described, are defined up to these gauge freedoms. So you shouldn't, if you rotate a phase, you shouldn't call it a new state. It's the same state. But the way you construct your Hilbert space, the way you construct these vectors is not always trivial. Sometimes they have very non-trivial topology, like in this case. So if you're trying to describe a vector, it cannot be thought of as, it should be thought of as some kind of a bundle which has two sections which have to be sued properly. Taking a gauge transform does not create a new wave function. One must keep in mind it's the same state. And all I'm saying, like if you have this gauge transform gives me the same thing. But what's happening over here, this is happening over here at the equator. It's not about what happens at the singularities. So equator, everything is completely irregular. It's just that you have two things which have to be passed properly. And that's imposing this condition. And one can describe them in terms of a winding number. Essentially, you have this map, you go around phi once, and what you create over here, how many times you can wrap? You have to wrap fully. So how many times you wrap is this m. And you cannot unwrap using a gauge transformation. It's like topologically protected. So by the way, okay, I'll come to this. This thing that you have to choose two sections actually should be very familiar to you guys, because if you take a state of a two-level system on the block sphere, in terms of theta and phi, you cannot describe it using a global section. You always have choice. Either you have a problem on the north pole or on the south pole. It's the same thing. And you can do the same kind of analysis over there, that you have to choose either the upper one or the lower one, and the two are connected with each other through this kind of a gauge transformation. Should we take like 5 minutes break? And if there are any questions, let's take a 10 minutes break. अभी ये माइक बंद कर दें. Phase vector. This must shift by multiples of 2 pi. So you can think of it like you're putting one rubber band on top of the other. You cannot stop midway. So you can wrap many times, but you have to have complete wraps.
So we'll start at 527.
5, कितने?
520. It's 527, so 537.
540.
540.
Get the correct flux, but I think I will discuss it probably in the end. Right now, let's discuss the second topic of the day, which is kind of very related to what we have discussed so far. So that's Berry's phase. So this is related to what is called adiabatic theorem or adiabatic dynamics. And the idea over here is that suppose you have a Hamiltonian which depends on a set of parameters. So if I dial up these parameters, if I change these parameters, the Hamiltonian is changing, and the new Hamiltonian is going to have some probably different spectrum and different states. So maybe these are states of your original Hamiltonian. Then we have this adiabatic approximation or adiabatic theorem. I don't know, should it be called theorem or whatnot, but it's an approximation. So under that approximation, if it holds, what you expect is that as I change my parameters, my eigenvalues will change. But if my system is starting in a particular state here, it will remain in there. So my eigenvalues are probably evolving, changing into some other spectrum. But if I dial these up slowly, I'll smoothly move over to the corresponding state in the new spectrum. And in particular, which is very easy to verify experimentally, is that if you are in the ground state, then if you make an adiabatic change in your Hamiltonian, you will remain in the ground state. So you have this Hamiltonian, and it has its spectrum, which depends on these parameters. So what Berry discusses is that if I start in a state with certain parameters in the beginning, then I remain in the same corresponding state as my parameters change. So in particular, if this is ground, this will remain ground. But that's not the most interesting part. What is more interesting was Berry's insight that as this is changed, this acquires a phase. And the phase it acquires, well, you know, like even if I'm not doing any adiabatic change in the Hamiltonian, my states, if they are eigenstates, then they evolve by picking up these factors. So they have these phase factors. This is the time evolution of an energy eigenstate with these phase factors. Berry said that when the time evolution is happening, not only because of the Hamiltonian, but Hamiltonian itself is time dependent, then you will remain in the same eigenstate, but you can pick up some phases. It is not very strange to expect given this, but even further, he split them into two parts. This is called the dynamical phase, and this is called the geometric phase. So in what sense this is geometric? So suppose this is the lambda space of your parameters. What Barry found was, with this splitting which he came up with, is that if I start from here, move around, I am changing my parameters, and if I come back to the original value of the parameter, I would have picked up this phase as well, but this phase in that case would be time independent. So gamma n in a complete when you are back to the same values does not depend on time. It only depends on the curve which you have traversed in your parameter space. So in that sense, this is geometric. And then there are, you can think of situations where this phase is very much suppressed, it's not relevant, then this phase can be of great experimental significance, and this plays an important part in all the theory which we will discuss later on.
Like in the usual description of adiabatic algorithms, it's the evolution that's of more interesting bit, right, rather than this phase. If
Well,
it's standard quantum algorithm discussion.
Both things are interesting. It depends on what's your purpose at a given time.
Like this phase wouldn't usually play a part in the standard description of quantum computation, right? If you're doing a standard adiabatic evolution, wouldn't this entire phase be just a global phase? And
Well, but you can imagine, just like, even in this two-slit experiment, what's really happening? You are splitting up your state where you can maintain a constant phase difference, right? And that gives you rise to your interference. Now, suppose you prepare identical states. Lambda 0, it remains over there, while the second state, you make it go around and it picks up a phase, and then you make an interference. So it will show up in that kind of experiment. You make a coherent mixture, and some part of it you let it go to, let's say, some magnetic field which acts adiabatically, and it causes it to pick some phase, and then you haven't destroyed the coherent mixture which you had created. It's just that one part is picking up phases, the other part is not.
oh, okay, got it.
Okay, so that's the main idea, and let's have a look how this comes about. So let me derive this formula because this is extremely important in what comes later. So suppose I start with this Hamiltonian. So it will have spectrum depending on the parameters, and the parameters are depending on time. So at any time, at any particular time, I can make an orthonormal basis. So I do have this basis available at using the states of any particular time. Now, if you pick this ansatz, to start with, it's just an ansatz that my state is going to evolve and can be written at any time like that, where you are assuming this form for theta. Where this is motivated from this factor. Since the energies are changing, so you're just kind of generalizing it. And for now, it's just an ansatz. So you're just going to put it in your Schrödinger equation and see, can you solve the evolution in some approximation. So I plug it in my Schrödinger equation. And on the left hand side, I'm just taking a bunch of derivatives. So I'm taking this and plugging in there. d by dt. So I'm going to suppress for now that dependence on lambda when I don't need it, just to write a bit quickly. So because of this ansatz, when I take the derivative of this integral gives me these e's. And that's helpful to cancel things on the other side. Because the other side is now because Hamiltonian at any given time is going to pick up the energies. these two cancel. And I get this equation. Let's use some other color. So this is the equation I get, and I project it psi m. So if I project it to psi m, from here I'm just going to pick up Cm dot and E iota dot E iota theta. And on the right hand side, what I'm going to have, not much, I have to just write it as a projection. Like this. So Cm is this. Let's call it A. Dot किस पे? Cm पे. Now I start with the Schrödinger equation. Well, this was the Schrödinger equation, the eigenvalue equation, and take a derivative over there. So I start with this. They're all t dependent. And differentiate. So I get dh over dt psi n plus now I project this with, because this is for a particular n, choosing m not equal to n. So I get psi m, this term and this term over here, this just gets 0 because this is projected. This is just outside. So this becomes 0. And I get so it is this guy which I want to put in here from this equation. So I have this can act over here and pick a EM. And so then this will become exactly like that term. And I will have an En minus Em, right? So this picks up an Em, take it to the other side, you get an En minus Em. And then this term is left. And I have En minus Em. So you put it back in here. You get this term because in the sum over there I said m is not equal to n. So this term is separate. And then I have this term. Cn, that junk. Now the adiabatic approximation comes in here. I'm not going to justify it except through this small thing that it involves changing Hamiltonian, rate of change of Hamiltonian, and if it is slow enough, then you can put it equal to 0. But in practice, obviously, to justify for certain specific systems, you have to be much more careful, compare the rate of change with some internal frequencies which are generated by these evolution of these states. But that's what adiabatic approximation is, that when the Hamiltonian is changing slow enough so that you can neglect it. And this is all there is now in the dynamics. So this is your equation. And whatever it has in front, then a formal solution for this you can write So the way they write for the Babar phase, they pick out an iota. So that means this gamma mu of t is and if I assume that I started in a particular state, let's say state n, so if the initial condition is Cn is 1 and all the Cm other are 0, then your evolved state would be, you have this just from your ansatz, you have this guy which we just defined, and this is your nth. I should probably write with a lambda. Nth eigenstate of your Hamiltonian. So what adiabatic evolution has done, it has kept you in the nth eigenstate, but you pick up these phases, which can be turned into something important by the kind of experiment I just talked about. Now, over here, let's look at this a little bit more carefully. This phase, this is the Babar phase. So now just doing what do you call it, chain rule. This is just going to be so I can rub these and change these as limits on these lambdas. Now over here, now if I say that I come back, then in the lambda space we came back to same point, and this will become And this you can also write using the vector calculus notation lambda dot d lambda. So this is just a sum, so I can write it as a scalar product. Now it has quite a close analogy to electromagnetic potential, the vector potential. So if I just call this vector, it has components in the parameter space. And then the Berry phase is just this. And this is mod 2 pi because I can always add a 2 pi in the phase that will not be detected. This I'm going to talk more about in a bit. So this is called the holonomy of this. If I think of it as this is a vector field, this is called the holonomy of the vector field along a certain curve. Now this has also even further, well right now it's just a vector, but it has kind of similar gauge freedom as in case of vector potential. Because I said that my final state, where did I write? Over there. I said that take psi n lambda to be your eigen states, and they are picking up these phases. But what is the phase of psi n lambda itself? It's arbitrary. So starting phase is arbitrary. So I can include an extra arbitrary phase over there and include that in the definition of this, this vector which I have just defined. This is called Berry connection. Connection name is just coming because in the language of fiber bundles, the vector potential is the connection on a principal G bundle, and something very similar happens over here. So I take, I can always have this. I can shift my states by this. So that means that this, if I, let's say if I don't stop, don't come back, this will have this, and this I can write as so I'm assigning an omega, an arbitrary omega, to each lambda, each point in the parameter space. And so in that sense, A is like this. And this is immaterial when I compute the holonomy, because in the holonomy, this goes away. When I make a complete circle, this goes away. Now you can also use Stokes' theorem. So I'm doing this thing. More properly in the language of differential forms. So I combine these two to write a form. So this is and this will be called the curvature, Berry curvature. But if you are not familiar with forms, we can see what does it look like in 3D, and it's just a generalization of that to higher dimensions. So in 3D, what you're going to have, that thing is just A dot dl. So you're applying the Stokes' theorem, which gives you del cross A. So suppose your parameter space is 3-dimensional or 2D, then you can use Stokes' theorem over there. And so this thing you can call, this is just names. This kind of a magnetic field, Berry curvature, or magnetic field. So what is telling you? Is telling you that in this space, there's some kind of fields are there, and this B field has some flux through the circuit which you just traversed, and it's this flux which is being picked up by your Berry face. Let's look at a quick example of the computation of Berry space. So if I consider a 2-level system, maybe I can just consider a spin, and this 2-level system I'm controlling using some external parameters. For concreteness, you can think of it, but it could be anything. Something like this. So you have in the ground states, the spins are aligned with this field B, and I emphasize it doesn't have to be magnetic field. It could be any two-level system with this kind of form. This is B, this is S. So the point is of the adiabatic theorem is that if I change the direction of magnetic field, it could literally be magnetic field and spin. So if I change the direction of magnetic field slowly, the spin will follow it. It will not move out of its state of being aligned to it. And if we do that, let's ask what is the Berry phase. Although it follows the magnetic field, it will pick up a Berry phase. So what would that be? So let's write the states. Well, we have down and up states. Doesn't matter which one you call down or up. Putting a minus sign will fix it. So it's just a two-level system. You have only two eigenstates. Now this state, you might not have thought of it this way, but this state has a problem at the north pole. At the north pole or at the south pole. So at theta equals to pi, yeah, this has a problem at the south pole. Because if I put theta equals to pi, I get a 1 over here. But this E iota phi, can take any value depending on which side I come from. So it's not well defined at the south pole. But on the north pole, this is totally fine, because at the north pole theta is 0, this becomes 0, so it gives me a unique vector. It gives me 0, minus 1. So that for this reason, I'm going to call it the north state. This is also north. But if you want a state which is well defined on the south pole, you can consider this one. Very similar. Just bring the phase down here. And how did I get it? I just multiplied with e to the minus iota phi, because I can multiply with global phases. But now I can think of it as this kind of a gauge transformation. So something similar is happening, like you have the states are sections, and you need two sections to describe them. So I'm thinking of this as a gauge transformation. let us calculate the Berry phase of, let's pick this one. Cosine theta by 2 and e to the I phi So what I need to compute this thing, and let me write, this is not very bad. Because this is what comes in the computation of Berry connection. कहाँ लिखा है? Did I rub it? Yeah, I should have brought this down. कहाँ था? So I just want to get my iota straight. Anyway, so I have to compute this. This was my connection. And then I have to take the holonomy of this connection. So this gives me, this is not gonna be there because there's only two parameters theta and phi, and I get I'm just taking a derivative with respect to theta. Theta hat, then that term, there's no phi here, so that's 0. And when I compute this, so I'm projecting this on that. This with that gives me minus sine theta by 2 cosine theta by 2, and when I do with this complex conjugation gets rid of this, and I get plus so this whole thing cancels, and it's the only this term which is important. So the first gives me 0, and the second term gives me iota, phases cancel, sine square theta. Let me write it here cleanly. So this is the connection. किसी को याद है half angle formula? I think I wrote it here. You will get 1 plus or 1 minus? 1 minus So this takes exactly the form which I had for the monopole vector potential. And if I take the north state, I'll get, so this was north or south? Where is it? Where does it have a problem? It should be south, right? So at pi, this is singular. So somehow maybe I was careless in marking there. Maybe this is north, I don't know. One has to. And the other one will give you of course without the iota. If I take the iota out. And B is del cross A. I can compute it over there, but I don't even need to do that because we already did. So, because I'm carrying in my definition somewhere an extra I, so it's just there. So you have, I could have absorbed it somewhere. I can't locate in my notes right now. I have the numbers, but where's my 17? Because I removed that crucial formula. Where's my 16? नोट्स में देखेंगे मैंने बेरी कनेक्शन में कैसे लिखा है. I think I wrote it this way. Where B is like this. So if I plug it in, I get minus half R square this is the area element for the sphere, and I get half. So what I'm doing now? Well, I should draw it this way. My parameter space is a sphere parameterized by theta and phi. So the direction of the magnetic field, whatever you want to think of it. And I start from some direction, I go around and then come back. So suppose this has some area some solid angle omega. Which is just the area of this divided by total area. So I get everything is cancelling. I'm just getting this solid angle. And the reason is it's just like, what is the field over here? The field is that, B. It's a magnetic field, fictitious magnetic field. It's not that magnetic field. It's just what turns up in the parameter space of Barry, a fictitious field, you can imagine it. And it corresponds to a magnetic monopole. So there is a magnetic monopole sitting at the center. And it's the flux. It has a Coulomb-like field. And its flux through this is what you are measuring in the Barry connection. And the strength of the magnetic monopole is minus half. So it probably is going in. But also important that it's properly quantized. It's not arbitrary, it's half. And actually this is also very important. Why is this important? That I got a half here. And why did I get a half here? Well, the reason that you got a half here, you can trace it back to the analysis which we did in the case of magnetic monopole. That there was a Dirac quantization condition. So something similar happens here. When you try to patch up things, you get this quantization. And some hint of it, you can see it this way. So the Barry phase itself is going to be this. But remember, how did I got this flux? I got this flux by use of Stokes theorem. I said I go around this and I pick up I apply the Stokes theorem, convert this line integral to a flux through this. But who says choose this? You can choose this thing as the interior. In a two-dimensional surface with no boundary, interior and exterior are completely arbitrary. So I can use this to compute the flux. And if I use that to compute the flux, then the Barry's connection will turn out to be minus half the strength of the field. And quick calculation, I don't need to do all of that, just I know that because over there this area came about, now this area will come about. The rest of the solid angle. But with extra minus sign. Because now the area is not to the right of me, right of my transversality. It's not on the left, it's on the right. So it's in the opposite direction. So I'll get this phase. So I get 2 pi minus lambda over 2. Over here I had a minus here because of this. So if I exponentiate this to get my Barry phase, This doesn't matter. I get the same answer. And I got the same answer exactly because I had the magnetic charge half. It was, if it was anything else other than m by 2, if it were any multiple of half, then things will work out. But if it's not, then the two calculations will give me different answer, which will make no sense. So whatever we saw in case of magnetic monopole, it bears out over here, but not as a physical magnetic monopole, but rather a monopole in the parameter space. A fictitious magnetic field you can create in the parameter space, and it generalizes to higher dimensions as well. And this is a concrete example of that. So I haven't really thought what I'll do next time. Probably I'll try to change flavor, although we can go further in this direction. Maybe I'll discuss a little bit about Aharonov-Bohm effect. It's again a Berry phase, but it becomes topological. I'll try to do that quickly, and then discuss a little bit about the statistics. By statistics, I mean the spin statistics. When you exchange particles, what happens and what are the possibilities? So let me stop here. Any question? No question, let's just stop.
What's the identification for Wallace Magnus as a fictitious monopole? Like, it showed up in the math, but like, what's the reason why we said this is fictitious rather than actually real?
Because there's no magnetic field over here. There doesn't have to be.
If there's an effect that's showing up which can be attributed to something which looks like a magnetic field, then what's the criteria for distinguishing it as real versus fictitious?
Well, in what sense that you say that there are effects of magnetic field here? It's a construction which goes over in the parameter space. It's not affecting the dynamics of the particle the way the magnetic field was going to do. First of all, there is over here, you can think of it that there is an actual magnetic field. Is this related to that? And if yes, in what way? It's not related to that, because that magnetic field we moved around to get this thing. But this magnetic field was just sitting there, causing a flux. It didn't affect its dynamics through that movement. That was controlled by the other magnetic field, the real magnetic field. And we could have changed that magnetic field with some other interaction, right, as a two-level system. So then you would have that interaction, which you don't necessarily need to interpret as magnetic field. So it's not controlling the dynamics of the state in that sense. But there are certain situations. For example, in the Aharonov-Bohm effect, this magnetic field, I would say, I have to recall exactly, but it almost becomes same as, because there's an actual magnetic field, a magnetic flux, and magnetic potential, and the Berry potential becomes proportional to that, almost same as that. So in that case, I think, but in that case I would say it's just a coincidence in some sense.